It seems like we could add into the mind reading exercise at the end of last Tuesday. That the two objects, when they come together, what's common between them, and the force that they apply to each other, the magnitudes will be the same. And they'll touch each other for the same amount of time. So that's where we're gonna start. I'm gonna, of course, use shorthand notation because I don't feel like writing out a lot of words. So first, just start out with the fact that they will exert the same force, but the force they exert on each other are in opposite directions. So I have force on A from B. So we'll just write that. This is the force on object A by object B. And that's going to be equal to the negative of the force on B from A. It's just Newton's third law of motion. The equal and opposite bend, two objects will exert a force on each other in opposite directions at the same time. They're going to touch each other for the same amount of time. So whatever this force is, it's the same amount of time. I'm just going to multiply times however long A and B are touching. So the force on A from B times however much time it was is the force on negative force on B from A times however long they were touching. Newton's second law of motion, what does F equal?
Force.
Yes, it does. We got something,
Friction.
looking for Newton's second law, chapter 4. F equals, I believe I even labeled it as what I considered the most important equation in all of physics.
Total force.
Equals,
Mass times acceleration.
that's the one. So this force here would be the mass of A times the acceleration of A times time is equal to the negative mass of B times the acceleration of B times time. So all I've done is just take Newton's second law, F equals ma, and stick ma instead of F. What is acceleration times time?
Distance. Distance.
No. Let's connect it with what you just did. If I have an acceleration time graph, and my acceleration is constant positive. So this is some value of acceleration here, and for some amount of time, let's say this is 5 meters per second squared, and this is 10 seconds. So if I multiply acceleration times time, I get 5 meters per second squared times 10 seconds. The math part is 50, but what are the units?
Meters.
You said meters?
Yeah.
If you're stopping there, you know.
Don't the S's cancel out? No.
I got two of them, that's S squared.
Oh, okay, so meters per second.
Which are units of? Meters per second. Units of what?
Acceleration.
Acceleration is meters per second squared.
Distance? No.
All right, meters are a unit of what?
Measurement.
Some measuring what?
Distance.
Okay, so distance and seconds is a unit of,
Time.
so distance over time is,
Displacement.
I think somebody just said it. Velocity is what I was going for originally. Speed depends on how to interpret it, how you want to interpret it. In this case, that area, or acceleration times time, is not the velocity, it's the change in velocity. For those fans of equations, I know that acceleration is the change in velocity over the change in time. If I cross multiply here, I get acceleration times change in time is equal to 1 times change in velocity. This is what I was heading for. Acceleration times time is just equal to the velocity change. So, let's go back over there and substitute. So I'm going to take those two things right there. So I got ma times the change in velocity of A equals the negative mb times the change in velocity of B. Let's see how many times I kick it down there. All right, next step. What is change? How do I find the change in velocity? If I start out going 2 meters per second, and then I go to 10 meters per second, with positive, what is my change in velocity?
8.
How'd you get
meters
that?
per second. You subtract
What
Five.
minus what?
the distance, 10 minus 2. Or to find the difference in the numbers.
Okay. But I can find the difference between 2 minus 10 or 10 minus 2. Which one do I,
Initial versus final?
versus? So initial minus final or final minus initial?
Initial minus final. No, final versus initial.
Final minus initial?
Yeah.
Okay. Change. This is one of the few always. Change. Always. Final minus initial. It is 8. Change is positive 8. All right, so this is mass of A times the velocity of A final minus the velocity of A initial equals negative mass of B, velocity of B final minus velocity of B initial. The next step is going to have the most writing, and then we're going to start simplifying. Questions up to here. What I did is I just, instead of change, I wrote it out as the final value minus the initial value. And this is supposed to be a V over here.
And we're calculating the force of 2 objects.
Well, we started out with force acting between 2 objects, and then multiply times time, and we're just slowly taking this original concept here, that Newton's third law is true, and they touch each other for the same amount of time, and we're just taking it to, I was about to say a natural conclusion, but basically where physicists usually take it.
What do physicists use this for? I'm just.
We're getting there. It's
Okay.
actually, it's going to come upon an incredibly powerful equation.
Okay.
We're getting there.
Okay.
Now I'm gonna distribute, and this is the most writing, and then we're gonna cut down on it. So distribute, I got something in parentheses here with a plus or minus, and something multiplied outside, so I multiply this times each thing inside, so I get mass of A, V, A final, minus mass of A, V, A initial, equals negative mass of B, V, B final, plus, because I got the minus times the minus, M, B, B, B initial. All right. This is the point where physicists go, man, that's just too much writing. We've got to simplify it somehow. Give people a chance to catch up. Juliana, need help with any of this? You're looking like you're straining to see it.
Oh, no, I can see it.
Okay. Now notice we have mass times velocity. 4 different flavors there. We have mass times velocity, mass times velocity. So mass times velocity, what I'm gonna do is I'm just gonna go, you know what, I don't feel like writing mass times velocity, so I'm just gonna come up with another letter, P, to equal mass times velocity. And so this equation here, we end up with just P A final minus P A initial equals negative P V final plus P V initial. So instead of writing NV, we're just going to use P. And I will explain and yet not explain why P in just a moment.
What is the subscript on the second P?
That's AI for of object A and an I for initial. We're getting close to the end. Next step is I've got now this, whatever P is, I got this initial and final stuff. I'm gonna get all the initial stuff on one side and all the final stuff on another. So I'm gonna bring, that's a B there. I'm gonna bring this over to this side and bring that over to that side. And in order to do that, I have to undo it from over here, so I basically have to add this to both sides and add this to both sides. It's gonna cancel out the PAI over here and put it over there. This one, it'll cancel that on the right side, move it to the left. So I now have PA final plus PB final equals PA initial plus PB initial. Now, as a physicist, you come upon this and you're going, wow, there's something incredible there. Now, I'm guessing that most of you are not looking at it and going, that's really incredible. Maybe I'm just misjudging. Whenever you can get something where you have all the initial values, the sum of all the initial values on one side equal to all the sum of the final values on the other side, this is known as a conservation law. Whatever P is, if I add up all the initial values and I add up all the final values, they are equal to each other. So this is a conservation law. And now, what exactly is P? This, mathematically, is just mass times velocity. But we have a special name for it. It is known as momentum. And this is conservation of momentum. So, why P? Well, P is the letter that is used for momentum. Which might bring up the question of, why is P used for momentum? I don't know. It is the letter that is used even in graduate level textbooks. P is what is used for momentum. I've seen videos where people tease you with a title that they're going to explain why P, and they usually say, I don't know. I have seen it one place and it didn't stick. It's, I think, from the Latin for something, but I can't remember where it is. I think we can blame Descartes. All right, let's talk about how this is powerful. While they're interacting, I don't care what's going on. I know what happens before they hit. I know what's happened after they hit. While they're touching is irrelevant. So if you were faced with the following problem, you have a 3 kilogram mass traveling to the right at 4 meters per second. And you have a 10 kilogram mass heading to the right at 1 meter per second. I'm going to tell you that they will collide and stick together. If they stick together, if they stick together, it is a perfectly perfectly inelastic equation. I often will just write that as PIC. If you see perfectly inelastic collision, they're going to hit and stick together. We can now predict how fast that they will be going after the collision. So let's start out with, so I'm going to add up all the momentums beforehand. So first off, what is the momentum of this 3 kilogram mass before the collision?
3 kilograms? Is it the mass of the box?
Momentum.
The mass times the velocity.
Yep.
So 3 times 4, 12.
All right, so the momentum of the 3 kilogram mass before the collision initially is the mass, 3 kilograms, times the velocity, 4 meters per second, which is 12 what? Other people can take a guess, doesn't have to be Monica.
Kilograms per meters per second doesn't make sense.
So close, so close. You threw one too many pers in there.
Kilograms. Kilogram meter per second.
Yep. 12 kilogram meter per second. What is that in shorthand? What is the one word unit that we can use for this? There is none. They have not decided to name it to do that yet.
But it means momentum, right?
It is, the momentum is 12 kilogram meters per second.
Okay.
All right, let's do the other one. So the momentum of the 10 kilogram object initially, well, I do the mass, 10 kilograms, times the velocity, 1 meter per second, and I get
10. Kilograms is meters per second.
So what is the total momentum before the collision? Which I will just write as a capital P, which looks a lot like my lowercase p's, initial. The total momentum beforehand is
22. It wouldn't be squared. The
Pardon?
kilogram meters per second. It would just be
Yeah.
that.
Yeah.
Okay.
People let it sink in for just a moment. They're going to collide and stick together. So the question is, after the collision, what is their total momentum? A number of you know it. A number of you could take a wild guess and probably get it. What is the total momentum after the collision?
And the 22 was the momentum at the collision.
Before.
It was before.
What is it after?
Zero.
Not zero. If it were zero, that means that they came to a stop, and they would not stop.
32.
No. So miss it. I didn't hear the whole thing, but it didn't sound like you ended on the right syllable. So I'm gonna guess no. All right, conservation. Conservation in physics is the total before equals the total after. So what is the total momentum after they collide?
22.
It is the same thing. This is the power of it, because what's happening while they're trying to get to the same velocity, I don't know, it doesn't matter. What matters is I know what happened beforehand, and so I know what happens afterwards. Now I'm trying to figure out the velocity afterwards, so it's one object, they stick together, so it's now one object. That momentum final has to equal the final mass times the velocity. What is the final mass? Yeah, nice. Add 'em. So that's going to be equal to 13 kilograms times whatever the final velocity is. That's a 13 there. And so the math problem we have right here is 22 equals 13V. That's the math problem. How would you solve for V?
Divide by 13.
So V is, so my final velocity is whatever 22 divided by 13 is. So 1.69
69. Yep.
units.
So for, kilograms? No.
Meters per second.
Yes,
Oh, yeah.
that 22 is kilogram meters per second, that 13 is kilograms, so the kilograms would cancel out. If we just use straight up Newton's second law, we'd have to figure out how the force changes over time. I will tell you that the force changes over time is not constant. And so it becomes very difficult to use F equals ma. But we don't have to in order to predict the final. We just have to know what happened beforehand, and we can predict what happens afterwards. Do not care what happens in the middle. Questions to hear?
So the way that this question would be set up and like written out, let's say on like the master set of a
Right.
chapter, what would the original question be? If
I have,
it's like multiple parts, I know that, but.
the question would